Let's take a look at the homework that we had last night on page 494, not on page 495. Question number 1 was just like the example that we did in class yesterday. Question number 2 is a bit more challenging. I want to take a quick look at some of the things involved in question number 2. Maybe not do the whole thing in detail right now, but take a look at where we would go with it. And then in a little while, we'll go back and do that type of question. Okay, question number 2 is meant basically to see if you can go out on a bit of a limb. Question number 2 is meant to see if you can figure something out yourself with kind of the background that we have based on what we've learned this year and what we've learned last year. Number 1, a little bit more straightforward. Let's do number 1, okay, whether you think you need it gone over or not, just because it's a good little review question to go over here. It says a 0.058 kilogram firecracker that's at rest explodes into 3 fragments. One of these pieces goes to the north, one goes to the east. Where's the third one going to go? Here's my explosion point right here. We'll mark with an X. We've got one piece that's going to the north, and that piece, we'll call it number 1, 0.018 kilograms, and it has a velocity of 2.40 meters per second. We have another one that's going to the east. Okay, object number 2, it has a mass of 0.021 kilograms and a velocity of 1.60 meters per second. Where do you think the third piece is going to go? Let's not worry about the angle here. Let's take a stab at the general vicinity, which is going to go here down.
Downwards.
Yeah, we know it's going to go downwards to the left, right? If the total momentum before this explosion takes place is 0, then the total momentum afterwards has to be 0. If we have a momentum to the right before the collision, or a momentum to the right after the collision, then in order to give me a total momentum of 0, then I also have to have a momentum to the left. If I have a momentum upwards, then I also have to have a momentum downwards to give me a total momentum of 0. So we know it's going to go down and to the left. Having said that, if you drew number 3 wrong, let's say you drew number 3 up here, you'll still get away with that. Okay, these ones we have to draw correctly. The third one, the one that we don't really know exactly where it is, we can get away with drawing it wrong. It just is a little bit harder to visualize the question if we draw it wrong, that's all. All right, so where do we go with this now? Well, we know that we've got to do x and y components. Pi is equal to Pf. The total initial momentum is 0 because it's at rest. What if this firecracker was moving? When we see firecrackers exploding, usually it's in the air, and they are moving as they explode. What would we do in that case? We'd give it an initial momentum. Instead of being m1 v1i plus m2 v2i equals mvf, because 2 objects are colliding and sticking together, it would be mvi equals m1 v1f plus m2 v2f, and so on, because one object would be splitting up. Okay, we'd include that mvi if there was an initial velocity. There isn't here, so we'll just make the total momentum 0. m1 v1f plus m2 v2f plus m3 v3f, because there's 3 objects. Now, these objects don't have the same mass. If they did, could we cancel the mass out? What we want to do to cancel them out, what we want to see in order to cancel them out is that same mass in every term. Does it appear on the left-hand side? No, it doesn't. But since it's 0 on the left-hand side, it would still cancel out. Because in effect, what you'd be doing is dividing by that number, right? And when you go 0 divided by that number, it would be 0 still. So if the left-hand side is 0, it's as good as having that term on the left-hand side. But again, if you're not sure about that, then just don't cancel, because you can always get away with leaving the number there. Just as a little bit of extra work sometimes. Okay, M1 is 0.018 kilograms. V1F is what? What is it? V1F for the x component. 0. It says 2.4 right there. How do we get 0 if it says right in front of us it's 2.4? Because we're looking for the horizontal component right now, the x component, not the y. So we're going to cross that off. M2 is 0.021 kilograms, and V2F is 1.6, because all of that 1.6 is on the x-axis. M3, we don't know its value, but as in our example problem that we had yesterday, we're just going to do a little subtraction. 0.058 minus 0.018 minus 0.021 gives me, what is that, 0.019? Is that right? Times V3F. Anyone have a value for V3F there? Someone's got to have that. Yeah. Negative 1.768. Negative because this goes over to the other side by subtracting, right? Now, we know that we've guessed right now when we predicted where it was going to go, right? Or at least we know that it's going to go to the left because we get a negative value for the x component of V3F. We also should get a negative value for the y component of V3F because it's going downwards. Let's check that and see now. For the y component, again, pi equals pf. Once again, because it's not moving on the y-axis, the initial momentum is 0. The final momentum is m1 v1f plus m2 v2f plus m3 v3f. M1, 0.018. V1F is what? We already said that it was 0 up here, right? So, but yeah, that's for the x component, it was 0. For the y component, what is it, Tanner? 2.4. If it was downward, we make it negative. Upward, we make it positive. M2 V2F is 0 because we're dealing with the y component, and you can see that object number 2 doesn't go up and down at all. M3 V3F, 0.019 times V3F. We solve for V3F here. What does that work out to be for the y component? Negative 2.273. Thank you. Again, negative tells us that it's down, which tells us that we drew our diagram correctly. Let's resolve these vectors now. We've got negative 1.768. We don't need to put in the negative now because the arrow indicates direction. 2.273. A resultant vector is drawn from start to finish. Make sure that you draw your arrows on your vector diagram, okay? Front to back or head to tail, and the resultant vector goes from start to finish. That helps you to determine where the angle goes so that we know where to calculate it. Tanner, question?
I have a question on
Yep.
how you know if you go left and right before up and down.
Good question. Good question. Let's finish this, and then we'll come back to that question, okay? Tanner's question, by the way, if you didn't hear it, was how do you know whether we go left and then down or down and then left? Okay. The simple answer to that question is it doesn't matter, but we'll address that in more detail in just a minute, okay? Okay, we want to solve for V. That's the resultant, the magnitude of the resultant vector. It's 1.768 squared plus 2.273 squared. And for V there, we get 2.9 meters per second. Now we want to find the angle here as well, because velocity is a vector. It's opposite over adjacent. That angle works out to be 52 degrees. And because it's south from west, okay, that angle is measured south of west, south from the west. We're going to say 52 degrees south of west. So that's a perfectly correct answer. Now, Tanner's question, what if we drew it the other way? What if we drew it this way? 1.768, 2.273. Well, first of all, you're going to get the same speed. Okay, the same speed is 2.9 meters per second. But when you calculate that angle, you're going to get 38 degrees. But it would be 38 degrees west of south, right? Because you're measuring it this time from the south, not from the west, like I was in this diagram. Which one's more right? They're the same. Okay, they both mean exactly the same thing. And I don't care which one you use. Just be careful. Okay, if it's a multiple choice question on a test or on an exam, you're not going to get both of those options. So if you get this one and it's not an option, then you better be able to convert it to this one, or vice versa, for that matter. All right, let's have a quick look at question number 2, okay? In terms of how we're going to set this thing up. Again, I don't want to finish this thing in detail. I just want to give you guys a little bit of a heads up if you were on the right track or not, okay? We'll spend a little bit more time on this type of question in just a little while here later today. Number 2 says, a 65 kilogram student on a 2.5 kilogram skateboard moves to the west. He jumps off the skateboard with a velocity of 0.38, 30 degrees south of west. Oh, I don't like that. Don't like that south of west thing. That bothers me. What's the velocity of the skateboard immediately after he jumps? Okay, so what do we got going on here? We'll make the total mass. We'll just call it M. I don't want to call it object 1 or object 2. You know what? Let's call it object 1, 2. Because it's the guy and it's the skateboard together. Yeah, I don't care what you call it, okay? I'm calling it 1, 2 just so that I remember that it's both of them combined, 1 and 2 combined. It's a total of, what is that, 67.7? 67.7 kilograms because it's the guy in the skateboard or the girl in the skateboard together here. Moving at 0.40 meters per second to the west. This is before the explosion, for lack of a better term, takes place. Now, the person, the skateboarder, jumps off the skateboard with a velocity of 0.38, 30 degrees south of west. So we're going to say object number 1 is going down this way. Okay, the mass of that person is 65.2 kilograms, and the angle here is 30.0 degrees south from the west, or south of west. Object number 2 is the skateboard itself. Where's the skateboard going to go? Where do you think the skateboard's going to go? Like this? Okay, remember this. Okay, we're trying to calculate where the skateboard is going to go. So if we guess wrong, it's not the end of the world. Okay, you're not going to get the question wrong necessarily because you do that. We have to get this part of it right because those are givens. But what we're solving for, we're just drawing in there to help us visualize it. Okay, it doesn't necessarily cause us to get the wrong answer. Where do you think it's going to go? Like this? Yeah. I think it's going to go up there as well. Having said that, there is a possibility, depends on how hard you jump off, that you could actually make it go backwards like this. Okay? So we're not sure. In some of the other questions we've done, we knew where it was going to go if we thought about it. Here, it could go either way. Let's guess there. I think I'm probably right. But even if we're not, it's not the end of the world. This mass, by the way, is 2.5 kilograms. Let's write that down. We want to find out what that speed is. And we also want to find out what that angle is. Well, we know that we do x and y components here, right? Okay, that's not going to change just because we got this funny angle of 30 degrees. This is one of those questions where before the explosion takes place, it is moving, just like if we said the firework bundle was moving. So we're going to say MVI equals M1V1F plus M2V2F. The total mass initially is 67.7 kilograms. The initial velocity we're going to say is negative 0.40 because it's to the left. M1 is 65.2. Now, what do we do with this V1F? This was 0.4, by the way, or 0.38, right? Let's write that down. What do we do for V1F here? Any ideas? Any ideas what we're going to do for V1F here? Okay, so I'm just going to see if anybody else had a thought on that one. Megan? Yes. Okay. We don't, basically, here's the rule. We don't like funny angles. We don't like angles of 30 degrees or 50 degrees or anything other than 0 or 90. So let's get rid of it. Let's do exactly what Megan suggested and turn that 30 degrees into an X and a Y. So let's do a little aside over here. Here's my 30 degrees. Here's my x, here's my y, here's my 0.38. So let's get x. Let's say cosine 30 degrees is equal to adjacent over hypotenuse. Megan, what did you get for that? 0.38 cos 30. Didn't get it? Can anybody else get the number? 0.19? Oh, yeah. That's 0.5, right? The y component is the opposite side. This one is a little bit harder to calculate. 0.38 times sine 30. 0.329.
Yeah.
So basically, what we could do if we wanted to is change this diagram to look like this. We've got an x and we've got a y now. Is that wrong? 0.32? This is 0.32?
Yeah.
Oh, yeah, it's backwards here, yeah. Yeah, this is 0.19, right? This is 0.19 for sure, because sine 30 is 0.5. Yeah, and then this is 0.329? Okay, thank you. So essentially what we've done is replace that vector that was at the funny angle of 30 degrees with two vectors, an x and a y. And that's a lot easier to deal with. Okay, now we can go back and say v1f is what? Oh, this is 0.329, right? This is 0.19. So v1f now, okay, remember green is object number one. v1f is what? For the x component. What is it? It is 0.329. We're going to make it negative, though, because it's going to the left, right? So negative 0.329 plus m2, which is 2.50 times v2f. Okay, I'm not going to solve for v2f here right now, okay, because it's not the point of what I wanted to show you here, okay? The point was, essentially, we treat the problem the same, but if we've got a funny angle, all we have to do is change it into a not a funny angle. 90 degrees or 0 degrees. We have to change it to an x and a y. Okay, does that make sense? We do the same thing with y, right? We went to the y component. v1f would have been negative 0.19 because it's downwards. Question?
Because I took like 180 and used 30 as a reference angle, not 210.
Say it again.
Okay, instead of using 30 as your angle,
Yeah.
for how I drew my diagram, it was in the third quadrant, second quadrant. Yeah, like that. So the 30 would be that, and I added 180. You do that every time for
So you added that to 180 and got 210
yeah.
for cosine and sine? You can, yes. I want you right now, guys, on your calculators to go cosine 210. Cosine 210. Negative 0.329, right? Let's go sine 310. Sorry, sine 210. What do you get? Negative 0.19? Oh, sorry, yeah, sorry. Multiply it by 0.38, right? And you get negative 0.19, right? So cos of 210 is the same except for sine, except for the sine of it, as cosine 30. Sine 210 is the same except for the sine of it, of sine 30. Okay. So basically what you're doing there, that's correct. Okay, but be careful with that because you might end up making a mistake with the direction there, okay? Essentially, here's what's happening there, okay? When you go cosine 210, you're using the positive x-axis as your reference point, okay? In a way, that's better, okay? Although it's a little bit more of a mathematical technique as opposed to a physics technique, but that's okay. In a way, it's better because it tells you that it's negative, right? When we go around here, it tells you that the x component is negative relative to this axis, right? It tells you that the y component is negative relative to this axis. Now, we use this axis as a reference point. Okay, we use the west axis as a reference point. Well, we're going to get a positive value, right? Because we use that as our reference point, right? So you already get the negative. right? Just be careful you don't add in a negative to what you get there, because it's already there if you're using this as your reference point. Okay, the danger with that is, A, you add in the negative when it's already there, and B, you don't really see the triangle there, right? Trigonometrically, is that a word? Trigonometrically. Sounds good if it isn't. Okay, we're going to make it a word if it isn't. Trigonometrically, it works out fine, and it always will. But you got to be careful with those negatives. Okay, so you guys see what you do with the y component, right? Once you've got x and y, well, then it's just the same as the other questions, right? Just combine them old-fashioned way. Okay, let's take a look at this one, page I don't know, 15 or so in your worksheet booklet, multiple choice question number 23. I'm going to have you submit this, please, as numerical response question number 1. All right, let's take a look at this question. I got the following answers from people here. I got 9.09 from a lot of people. I got 9. I got 0.91. All of those answers, people have done it correctly. They've just filled it in wrong on a couple of those answers, okay? And we'll talk about how you fill it in just a minute here. I also got 4 and 1.67. Those are wrong, obviously. We'll take a look at what you do with this question, first of all, and then secondly, how you're going to fill it in, and why 2 of those 3 correct answers would have actually been marked wrong on a diploma exam, even though you did it correctly. All right, this is a 2-dimensional collision, right? We got coal coming down this way before a collision. We'll call that object number 1. We've got a hopper car going this way before the collision. We'll call that number 2. The hopper car is moving at 2 meters per second, and it's got a mass of 1.0 times 10 to the 4 kilograms. You would expect the hopper car and the coal combination after the collision probably to go down this way, right? Does it go down that way? Yes, it does. How much, though, does it go down? A minuscule amount. How come? Because the Earth's going with it. But when the coal comes down, it not only pushes the hopper car down, but it pushes the Earth with it. So in the end here, the y component, there is an x component and a y component, but because the y component would have to include the mass of the Earth in the final mass, you're going to get a final velocity that is so ridiculously small, there's not even any point in doing it. Does that make sense? Essentially, we're only going to do the x component here because the y component is going to work out to be so small. Now, in the end, we couldn't even, with this question, do the y component because we don't know what the velocity is of the coal before it hits. If we did, we could do the y component. We could get a final velocity x and a final velocity y, but this one right here would be 0.000000 whatever meters per second, because we have to include the mass of the Earth there. For the x component, we don't have to include the mass of the Earth because the Earth isn't being pushed to the right, only being pushed down. Yep. Well, the problem is we don't know how high that starts, right? So we don't know how far it falls. It's a good point. Now, if we knew the height that the coal fell from, yeah, we could figure out how fast it was moving when it struck there. But I don't think, to be honest, that there is a way with this question to figure that out because of a lack of givens. Okay, so listen, there's nothing wrong with trying the y component, but you have too many unknowns in this question. And even if you didn't, you'd get an answer that was so ridiculously small that you'd throw it out anyways. So let's do the x component. Let's say pi is equal to pf. Let's say m1 v1i plus m2 v2i. We got the coal plus the hopper car equals mvf for the x component. M1, it doesn't matter because it doesn't have an x component. M2 is 1.00 times 10 to the 4. V2I is 2 meters per second. The combined mass here, we got 1.0 times 10 to the 4 plus 1.2 times 10 to the 4. That's 2.2 times 10 to the 4 times VF. When we solve for VF here, the x component, it works out to be 0.909 meters per second. Again, solve for the y component. It works out to be 0.00000000000, however many zeros that goes. You want to combine 0.00000000000 with 0.909, what are you going to get? 0.909. So there's no point even doing the y component, even if you could here. All right, so how do we express that? Well, it says to put it in scientific notation. And scientific notation is always 1 digit, decimal something. So it's going to be 9.09 times 10 to the minus 1. What are they looking for here? They're looking for the value of b. They're looking for this. Now, there were some people that just filled this in as a 9. Because automatically people think, oh, they're asking for b, they're asking for the first digit. No, they're asking for a 3-digit answer. They're asking for 9.09, not 0.91. Okay, scientific notation, it's 9.09. Does that make sense? Because the hopper car and the coal combine after the collision. So we've got to add the two masses together, the hopper car and the coal. Does that make sense, guys? Okay, we see these questions from time to time, not this exact question, but the idea that the Earth becomes a part of the system afterwards, right? Whenever the Earth becomes a part of the system afterwards, for the y component, just ignore the y component, because it's going to work out to be so small that it just doesn't matter. Okay, save yourself the bother of doing it. Okay? I want to do one more example here, and this is real closely related to question number 2 that you had for homework that we already looked at. So it's not going to be completely unfamiliar to you right now. This will be the last thing that we do today, give you a couple questions for homework, and then we'll call it a day. 19.6 kilogram curling stone, which is stone A, or I'm going to call it stone 1, is moving to the north at 1.2 meters per second. Okay, let's draw it over here so we have some more space to work. So object number 1, curling stone number 1, 19.6 kilograms with a velocity of 1.2 meters per second to the north. Curling stone B is at rest. Presumably it has a mass of 19.6 kilograms as well, but a velocity of 0 meters per second. Now it hits it off center. That means that we can cause it to move one way, not just straight forward. Okay, we know that curling stone A moves off with a velocity of east of north here. So it's going to be this way. Curling stone 1 goes this way, 12 degrees at a speed of 1.17 meters per second. Where do you think the second rock is going to go here? This way, right? Intuitively, you know that. Even if you're not a curler, you know that if you want to make curling rock 2 go to the left, well, you're going to hit it off center to the right. Same as playing pool, right, or billiards. Okay, we want to find out this. Well, the first thing we say here is, I don't like funny angles. So we're going to do the same thing as, I forget who it was that told me to do this in the last question. Was it you? No? Megan? Yeah, that's right, it was Megan. We're going to get rid of that funny angle. So let's kind of draw it off to the side over here. We got 1.17. We have 12 degrees. We've got an x up here and a y down here. We're going to say sine 12 degrees is equal to x over 1.17. That gives us 0.2433 meters per second. Notice this time I use sine for x. Last time I used cosine for x. Be careful about that. Cosine 12 degrees is equal to y over, this is the adjacent side over 1.17. For this one, we get 1.1444 meters per second. Now, if we wanted to, we don't have to, but if we wanted to, we could redraw our diagram to look like this. If it helps us to visualize it a little bit better, right? With an x component that's 0.2433 and a y component that's 1.1444. Okay, now let's do our thing like we've done here for the last couple of days here. The x component pi is equal to pf. The initial x component is 0. Even though you've got an object that's moving before the collision takes place, we know it's moving on the y-axis. Nothing is moving horizontally. So I'm just going to ignore both of those terms and put in 0. m1v1f plus m2v2f for my final momentum. Is there a shortcut here? Anybody catch it? What can we do here to make life a tiny bit easier for us here? Matt? Yes, because it's the same masses, we can get rid of it. Now, only appears on the right-hand side, right? But 0 on the left-hand side, so that counts. Right? 0 divided by m is 0. Makes life a little bit easier for me here. V1f for the x component is 0.2433. For the y component, for the x component of object 2, is going to be negative 0.2433. Now let's do the y's. This time I'm not going to get rid of those terms right away, or at least not both of them. This one I can, right, because it's at rest. And the masses cancel again, right? That makes life a little bit easier for me. It's the same mass in every term, 19.6 kilograms. That's a heavy rock, eh? Throwing down the ice. V1I here for the y component is 1.20. V1F for the y component is 1.1444. So for V2F, when we do, we get 0.05557. Okay, so let's redraw it. This is what we've done a dozen times before already. We've got an x component that is to the left, 0.2433. We've got a y component that's up, 0.05557. We draw the resultant vector in there, the angle in there, and then we do our thing. What is our thing? Scott, what are you going to do here? What are we going to do here, John? To get the angle, yeah, we're going to do opposite over adjacent. Okay, if you want to find the angle first, that's okay. Gives us 12.9 degrees. That would be 12.9 degrees north of west, right? And what are we, sorry? Go ahead. This would be north of west. Had you drawn it the other way around like this, you would have gotten something like 78 degrees, 78 degrees, something like that, west of north, right? And that would be okay as well. How do you do V there? How do you get the value of V? Right, this is the Pythagorean Theorem, right? So a squared plus b squared equals c squared. Anybody have that value? 0.25. How many digits are we supposed to be for this one? 3? So is it 0.25? 0.250? Okay. Is that okay? What's the only difference between this question and the other questions? Not question number 2 that we had for homework last night, but the other ones. The only difference is this little blurb over here, right? This little blurb over here. It's a little bit more work. We got a funny angle. 4 words. As soon as you see an angle that's like that, 12 degrees or 30 degrees or whatever, I don't like funny angles. I don't like funny angles. So get rid of it. Okay, here's your homework. Then I'll answer your question, okay? Yeah. Here's your homework. Let's do, you know what, let's just do the practice problems on page 498. Okay, the bell's going to go. You don't really have time to work on it in class here, so I won't give you everything that I was going to give you. 490, the practice problems on 490. I think this is 490. Yeah. All right, that's it, guys. Have a good day.